So, hello.
Yes, hello.
Okay. Va bene. So, the last remark on the subject, page 6, I think, of our file is the negation of some statement using the quantifiers. So we negate all the quantifiers from left to right. That is, if I have for all, then I will write there exists. If then I write there exists, then I have changed it for all. We will see this in our future studies. Now it's only a remark how to have the negation of some of some statement. So now we pass to the sequences. It's a page 7. So in some way, I can say that a sequence is some simple list of numbers x1, x2, x3, so on, xn, and so on. We will call the terms, the numbers in the sequence as terms of this sequence, so that x1 is the first term, x2 is the second term, x sub n is the nth term, and so on. As a subscript n 1, 2, 3, and so on, marks the position of the corresponding term in the sequence, and we will say that it is the index. Mainly in our future work, we are dealing with the real numbers, not with the complex numbers, but as for the complex numbers, I hope we can use the same thing. So first of all, as for its page number 8, I want to give you some examples of the sequence. The first example is very clear. If we have the natural numbers 1, 2, 3, 4, and so on, n, and so on, it's an example of a sequence. If you have with you your calculators, then you can find that on your calculator, if I try to divide 1 by 3, okay, then in fact we can approximate this number by the values 0.3, 0.33, 0.333, and so on. So in this way, we have a sequence. This, the third example is rather clear. So the sequence 0, 1, 0, 1, 0, 1, and so on. It's also the sequence. We have also the sequence of zeros, or if you want 0, 0, 0, or if you want, you can take a sequence 1, 1, 1, and so on. Finally, we also have a sequence like a geometrical progression. So 1 r, r square, r cube, and so on. You have also the sequence when the terms change their sign. So in this way, you see example number 6, it seems to me 1 over 2 minus 1 over 3 and so on, minus 1 to the power n over n and so on. So you see there is a number of sequences which are usually used in mathematics, but in this way, we are dealing mainly, but not always. When we can prescribe the nth term of the sequence in a direct way. You see, in these examples, for example, if you take minus 1 to the power n over n, this is the term which we want to call x sub n. But it is not always like this, because if you have, for example, the decimal expansion of the number which is irrational, or the number pi, you cannot say which is x sub n in this sequence. You have to write then that if you have n, for example, decimals after your point, you have to write that x sub n is something, 3 point, and so on. You see, it is no general term in this case. There is no general term. Finally, page 10. You have some recursive sequences. It is also an unusual way to define the sequences, and the classical example is the so-called Fibonacci sequence. If you know the book by Dan Brown, then here you will see also the Fibonacci sequence in this book. So by the formula 2.1, we write that the zero and the first term are 1, and then in some way we define our sequence so that the nth term is such that f sub n is f sub n minus 2 plus f sub n minus 1. And in this way, you can find all the terms of your sequence. So the question, if you turn your page to page 11, You see, the first question maybe we start always with the term when n equals 1. It is not always the case, so it is not very important because we are interested in the behavior of the corresponding sequence as n goes to infinity. So the first terms of our sequence, I say that is not very important. So, for example, here, page 11, we have a sequence x sub n, which is square root of n minus 2. You see, if we are dealing with real numbers only, so if I take n equals 1, the square root of minus 1 is a complex number and it is not good. So usually for the sequences like this, we will start with the number n equals 2. So the first term, x2, or if you want x0, so the notation is not very important, so x2 will be 0. Okay? Now, page 12. We are going to study our sequences, and the first notion, which is very important, is the notion of bounded sequence. So page 12, I say that a sequence x sub n is called bounded if we have two constants a and b such that xn is less or equals b and greater or equals a for all indices n natural. You see here, I do not use the quantifiers. I write this statement in words if you want. But now, if I want to use the quantifiers, I will write that there exist two real numbers a and b such that, you see, there exist two numbers such that for all n natural, we have that x sub n is between b and a. For example, you see why I say that there exists. Because if my sequence is bounded by 0 below, so xn is greater than 0, greater or equal than 0 and less or equal 1, then you see I can say that my sequence is greater or equal -3, -5, I don't know, -7. And also, if my sequence is less or equals 1, it will be less or equal 3, 4, 5, and so on. You see? So, at least, what I can say, that I have two constants, such that my inequalities hold true. Is it clear?
Yes, it's clear.
Good. So now, usually, we do not write these two constants, but we make use of the absolute value of my sequence. So I can write, for example, and page 13. So I write that my sequence is bounded if the absolute value is less or equals some constant C, capital C, for all n from the natural numbers. In terms of my quantifiers, I write the proposition, if you want the definition, my definition, better to say, my definition 3.1. So there is a constant, say, capital C, positive, such that for any n natural, we have the absolute value of x sub n is less than C. So it is exactly the same thing that it was in the first definition. Is it clear that it is exactly the same thing or not?
Yes, it makes sense.
Yes. So you see, if I have that my sequence is between 1 and -3, then it will be between -3 and 3, so the absolute value will be less or equals 3. So it's exactly the same thing, but because we will not to have an exact constant in this way. We want to say that our sequence is bounded. If it is bounded by 3 or 55, it will be the same thing. It's bounded. The final point in this way. So let's start with the exercises. So it's page 14. You see the exercise. I suppose that I have two bounded sequences, x sub n and y sub n. The question is, show that the sequence z sub n, that it is not a complex number, it's the third sequence. So Zn is defined as a product of xn, yn. So I want to show that this sequence is a bounded sequence. Then the second question, we want to show that the sequence z sub n given by alpha multiplied by xn plus beta multiplied by yn, where alpha and beta are real constants, So we want to show that n is also a bounded sequence. As for the statement 1, so what do we know? We know that if x sub n is a bounded sequence, then there is, you see, statement 3.2. Here I make use of the quantifiers in order to explain briefly what do they want. So, due to the definition As for the sequence x sub n, we know that there is a constant capital C sub 1 such that for all n natural, we have that the absolute value of xn is less than the 1. The same thing, I know also that for all natural n, the absolute value of y sub n is less than c2. It's by the due to the definition of the bounded sequence. Clear? Nothing else. Nothing else. Only the definition. So then, if I take the absolute value of my sequence z sub n, then it will be the product of absolute values of x sub n and y sub n. So from the estimate from formula 3.2, we have that the absolute value of Zn is bounded by the product of the constant C1 and C2. We can say C sub 0. This means that by the definition, our sequence Zn is a bounded sequence. Is it clear?
Yes. Yeah, that's clear.
Very good. So now the second statement. The second statement, we want to show that the linear, you see, I can say that alpha xn plus beta yn, it's a linear combination of two sequences, x and yn. So in this case, page 15, I think, page 15. So if I take my z, the absolute value of my sequence z sub n, then I have to take the absolute value of alpha x sub n plus beta y sub n. Now, I think you know that there is a triangle inequality. The triangle inequality. So if I have the absolute value of alpha xm plus beta yn, it will be less or equal absolute value of alpha xm plus absolute value of beta yn. Do you know this triangle inequality?
I believe I do, but it.
No, you have to know this. You see. Dear friends, dear colleagues. So if you have for real numbers the absolute value of a plus b, okay, absolute value of a plus b, it will be less or equal of absolute value of a plus absolute value of b. This inequality is called the triangle inequality. You see, you can find the proof anywhere on the web, but first of all, you can imagine, for example, if a and b are positive numbers, okay, so the absolute value of a plus b is exactly a plus b, and on the right hand side you will have that a plus b is a plus b. It is for the positive number. But if you try to check what's happened for the numbers, for negative and positive numbers, you will find this triangle inequality. You can find this inequality, I repeat, you can find this inequality on the web with the proof maybe, and then, okay, you will use this inequality in your future studies. So you have to know. Maybe it's the first time, but then, then. So if you have that your your linear combination less than absolute value of alpha x sub n plus absolute value of beta y sub n, then you will have that the absolute value of the product alpha x sub n is the absolute value of alpha multiplied by the absolute value of xn, and in the same way the absolute value of beta multiplied by yn is absolute value of beta multiplied by absolute value of y sub n. Is it clear or not?
No, yeah, that's clear.
It's not clear.
No, it is clear, yeah.
It's clear.
Yeah.
It's clear.
So 2 points here. The first one is the triangle inequality, and the second point is that the absolute value of the product is in fact the product of absolute value. So then, what do we have? We have that our linear combination, our sequence z sub n is bounded by a constant c sub 1, because our sequence x sub n is bounded, multiplied by the absolute value of alpha, because we do not know, alpha may be positive, negative, something, I don't know what. Then you have the same thing for your sequence y sub n, and then you see page 15, you have a linear combination of c sub 1 multiplied by the absolute value of alpha plus c sub 2 multiplied by the absolute value of beta, and this constant, it's a constant because alpha is a constant, beta is a constant, so it will be our constant c sub 0, and the absolute value of my sequence z sub n is bounded by this constant. So we have proved that the linear combination of two bounded sequences is also a bounded sequence. Is clear?
No, this C0 is equal to this expression, yes? Or
Yes,
it's only a constant.
Exactly. So it's only, you see, it's only a notation, nothing else. Because I have two constants, c sub 1, c sub 2, and two constants, alpha and beta, and then I define my constant c sub 0 in this way. So if you want, I know that my sequences are bounded by something, say C sub 1, C sub 2. Then I show you the constant, in this case C sub 0, which is a bound for my sequence Z sub n. You see? I show you the constant explicitly. We find this constant in our argument, in our work. You see? It's clear. So knowing that my sequences are bounded by C sub 1, C sub 2, I show that I can present you a constant C sub 0 such that the absolute value of Z sub n is bounded by C sub 0. So I give you C sub 0 explicitly, in an explicit way.
I understand, yeah.
Understand? It's clear.
Yeah,
Yes.
it's clear.
Clear?
Yes.
Yes? Good. Now, we turn our page in order to deal with some sequences. It is exercise number 5. So the first sequence is x sub n 2n square minus 1 over n square plus 1. So let's discuss. We want to show that this sequence is a bounded sequence. So I write, first of all, that xn, that is 2n square minus 1 over n square plus 1. First of all, it is strictly positive. Is it clear that this sequence is strictly positive? Because the problem of the sign of this sequence depends on the numerator of the fraction, yes? So if I take, because here we see that we have 2n square minus 1, okay? So if I take n equals 1, then the first term of this sequence will be positive. Yes, 2 minus 1 is 1 greater than 0. So if I take n equals 2, 3, and so on, the numerator of my fraction will be also positive. That is, for all natural n, the numerator is positive, the denominator is also positive, so my fraction is always, for all n, is positive. Clear?
Yes.
Yeah, it's clear.
Yes, it's clear.
So now I want to estimate my fraction. So you can imagine, if I take a fraction and, for example, 3/2, okay? And I take instead of 2, for example, 1. So I take that my denominator is of my new fraction is less than the denominator of my initial fraction. So if I take the fraction 3/2 and the second fraction 3/1, then the second one is greater than the initial one. Is it clear?
Yes, that makes sense.
Yes, very good. So here we have exactly the same situation. I do not touch the numerator of my fraction, but instead of n squared plus 1, I take only n squared. Then we have that the initial fraction is less than 2n squared minus 1 by n squared. Exactly like in my example, 3/2 and 3/1. You see, I take the denominator which is less than the denominator of the initial fraction. It's a usual trick, this kind of estimate. So if you have some questions, please. If it is not rather clear, is it clear?
Mm-hmm. Yes, sir.
Yeah? The girls, is it clear?
Yeah, it's clear.
Clear. So we take our denominator less than the denominator in the initial fraction. You see? Then our fraction will be greater than the initial fraction. Okay? So here I have 2n squared minus 1 divided by n squared. Dividing each term of my numerator, I will have that it will be 2 minus 1/n squared. You see, you have the difference of two positive numbers. Then I can say, at least, I do not care about the exact estimate, but at least 2 minus 1/n squared will be less than 2. This is clear, this point. So if you want 3 minus 1 is less than 3.
Yeah, I got it.
Okay? Clear?
Yeah.
Clear. So you see, you have that your sequence x sub n is greater than 0 and less than 2. So this sequence, due to the first definition of a bounded sequence, is bounded. If you want to exploit the second definition, you can write that your sequence x sub n is greater than -2. and less than 2. Then in this way, the absolute value of xn is less than 2. You see?
Yes.
Yes. Really? No problem. Clear?
Yes.
Maybe we
clear.
can see another similar example so we can get it to understand a
No,
little
no.
bit better.
Where is the question? Listen, where is the question? What you do not like? I say. So the first
The
step,
second fraction is where, because you have 0, you have the initial fraction, and the second fraction is -1, or what is it?
stop. You see
In the inequality.
the inequality. So why it is strictly positive, it's clear, I hope.
Yeah.
No problem. So in our fraction, I change the denominator. The denominator. It was n squared plus 1. It becomes n squared. So if I take a denominator which is less than the denominator of the initial fraction, the whole fraction is greater than the initial fraction. Are you agree?
Yeah.
Yeah. Then the only thing, I divide two terms of my numerator by n squared. So I have 2n squared by n squared is 2 minus 1 over n squared.
Yeah.
Yeah. So here you have 2 is a positive number. 1 over n squared is also a positive number. So at least, you see, I do not want to find an exact constant here. But I can say, for example, if you take 3 minus 1 or 5 minus 2, 5 minus 2 is less than 5.
Yeah.
It is, here we have the same situation. You see, you have 2 minus something positive. So it will be less than 2.
Yes, clear.
Yeah, good. So let's consider the second example. Maybe we will have, it will be more clear. So the second situation is xn is 1 minus n over square root of n squared plus 1. It is page 16, I think. So let's turn our page. In this case, you see, in this case, our sequence is not positive. X sub 1 is 0. X sub 2 is something negative. So in this case, it's better to study the absolute value of our sequence x sub n. So we turn the page and we have, you see, the absolute value of x sub n is less than, is less than. It is not necessary to write less than, it is exactly equals here. Equals the absolute value of 1 minus n over square root of n squared plus 1. So the first step in this case, first of all, I want to estimate the numerator of my fraction. So I claim that the absolute value of 1 minus n is less or equals n plus 1, or I write here 1 plus n. Is it clear or not?
It's clear.
Clear.
Yeah, it's
So
clear.
here, you see, if you want formulate, we make use of the triangle inequality, So the numerator is bounded by 1 plus n over the square root of n squared plus 1. Now, as for denominator, like in the previous example, we take the denominator which is less than the denominator of this fraction. So we forget about 1. Then we have that our fraction is bounded, is less than 1 plus n, but divided by the square root of n squared. Okay? We take the denominator, which is less than the denominator of the previous fraction. So if I take the denominator square root of n squared plus 1, and then I take the denominator square root of n squared, I forget about 1. Okay? Then square root of n squared is n. So I have exactly that the numerator of my fraction is 1 plus n, and the denominator is n. Is it clear?
Yes, it's clear now.
Clear?
Yeah, it's clear.
Yes. Good. So now you have a fraction which is 1 plus n over n. Then, dividing each term in the numerator by n, I will obtain 1 plus 1 over n. So here it is not exactly the same situation because you have a sum of two positive numbers. The first one is 1, so no problems. But the second one, you see, you have something like 1 over n. So it is clear, I hope, it is clear that for any n, for any natural n, 1 over n is less than 1. So if you take, you see, if you take n equals 1, good, 1 plus 1 is less or equals 2. If you take n equals 2, 1 plus 1 over 2 is also less than 2. And so on. If you take any natural number, the sum of 1 plus 1 over n is less than 2. less or equal. Okay. Is it clear?
Yes, it's
Clear.
clear.
Good. So I hope, I think for today it will be the last example, and then you will be free. So you turn the page, and we will try to okay, we return a little. So for example, this this exercise number 5. I think in your lectures you already know what's the limit.
Yes, we learned that.
Yeah. So you see, if I take my x sub n like 2n square minus 1 over n square plus 1, can you find the limit in this case? If n goes to infinity, can you find the limit? Who knows? Who knows? Hmm? So how to find the limit here? It's not our subject today, but if I divide the numerator and the denominator by, I say, the largest term, in this case, by n squared, I will have 2 minus 1 over n squared in the numerator, yes, and 1 plus 1 over n squared in the denominator. So this sequence, 1 over n squared, when n goes to infinity, goes to 0. Yes?
It's not muy clear.
Okay, we will see this later, not for today. I will explain you, and we will return to our I say to our exercise. So page 18, So you have a very sophisticated sequence, something like 5 n to the power 6 plus 6 divided by n to the power 4 plus 1 multiplied by n square minus 1. And here we will assume that n is greater or equals to. So first of all, I hope that it is clear that n to the power 4 plus 1 is greater than n to the power 4. So we have a sum of two positive numbers, and then n to the power 4 plus 1 is greater than n to the power 4. Clear?
Yes, that was clear, yes.
Yes. So in this case, 1 over n to the power 4 plus 1 is less than 1 to n to the power 4. So, for example, if 5 is greater than 3, then 1 over 5 is less than 1 over 3. Exactly same thing. Clear or not?
Yes, clear.
Clear.
Yes, yes.
Clear. So now, there is another thing, another inequality. We can use this inequality. This inequality reads that n squared minus 1 is greater than n squared over 2 if n is greater than 2. You can check this. You can check this. For example, if you take n equals 3, then 9 minus 1 is 8. 9 minus 1 is 8. And n squared over 2 is 9 over 2, 4.5. So you can check this by the mathematical induction, but really it is rather clear. You see,
Why do you put other inequality? For example, I can say that n2 minus 1 is less than n2, no?
you have to estimate, as in the previous exercises, you have to estimate your denominator. So
Okay.
you see, I want to estimate 1 over n squared minus 1. So in this way, it will be more useful to have the estimate like this. But you see, I do not want to find an exact estimate. So if I write that n squared minus 1 is greater than n squared divided by 15, it is also good. By 15, 16, 78 or something, by a constant. You see? Then, what can we write? We can write that x over n, which is defined in the formulation of our problem, is less than, as for the numerator, first of all, I say that in the numerator we have 5n to the power 6 plus 6, but if we have that n is greater than 2, then 6 is less than n to the power 6. You see, n, for example, n equals 2, 2 to the power 6 will be greater than 6. And for all natural numbers beginning by 2, it will be the same thing. So I can write that my numerator is less than 5n to the power 6 plus n to the power 6. Is it clear?
Yes, yes, it's clear.
Clear? The goal is clear.
Yes, it is clear.
Clear. Now you see, we have our auxiliary work as for the denominator. So the first term, 1 over n to the power 4 plus 1 is bounded by 1 over n to the power 4. And the second term, 1 over n squared minus 1, due to our inequality, is bounded by 2 over n squared. You see? Is clear or not? So you have,
Yeah, I understand it, yeah.
you understand. Good. We go. Monia, is clear.
Yes.
Good. So you have now the inequality 2 multiplied by, in the numerator, you have 6 multiplied by n to the power 6. Okay? And in your denominator, you have n to the power 4 multiplied by n squared. Then simplifying this fraction, we have 12. You see, 12.
Yeah.
This means that our sequence is bounded because first of all, you see, x sub n is less than 12, but from the other hand, it is positive. So it's bounded. It's a bounded sequence. Is it clear?
How did you convert the 6 to n 96 in the final sentence?
You see, you have in the numerator 6 multiplied by n to the power 6. Yes?
Yeah.
And the denominator, what do you have? You have n to the power 4 multiplied by n squared. It is exactly n to the power 6.
Yeah. No. But in the first sequence, in the 5m to power 6 plus 6,
You see,
and
okay.
you put
I understand your question, maybe. You see, I say that 6 is less than n to the power 6 if n is greater than 2.
okay, yeah.
Agree.
Yeah.
So 5n to the power 6 plus n to the power 6 is 6 to the power, or 6 multiplied by n to the power 6.
Okay, yeah.
Clear?
Yeah, it's clear.
So in this case, we have that our sequence is a bounded sequence. Is it clear, these examples? Or you have some questions?
Yeah,
Yeah, it's clear.
Clear?
Yeah.
So it will be enough for today. You are tired. Have a good evening. See you on Friday.
Thank you a lot.
Thank
Thank you,
you.
Professor.
Thank you. Ciao, ciao.
Ciao.
Ciao, ciao.
Thank you, teacher.